Hi everyone, welcome to VLSI for everyone. This channel is dedicated to make VLSI concepts simple and accessible for beginners. In today's video, we are going to understand what a D flip-flop is, why it is important in VLSI design, and then we will write the Verilog code for both synchronous and asynchronous D flip-flop. Finally, we will also look at how the design appears after synthesis. In this video, we will cover three things. First, the concept of D flip-flop. Second, the Verilog implementation. Third, the synthesized output. So let's start with the basic concept. What is a D flip-flop? So this is the basic diagram of a D flip-flop where D is the input, clock, and Q is the output. Now if we look at the timing diagram of the D flip-flop, here at the first sampling edge, the value of D is 1. So the value of Q also becomes 1. When the next sampling edge comes, the value of input D is 0. So the value of Q also becomes 0. Similarly, in the third clock edge, the value of D is 1. So the output Q also becomes 1. So this is the basic fundamental understanding of a D flip-flop. Now, why the D flip-flops are important in VLSI? In VLSI, flip-flops are everywhere. They're used to build registers, pipeline in processors, finite state machine, shift registers, and counters. Basically, whenever we need to store data between clock edges, we use flip-flops. They also play a very important role in timing because of a digital system often depends on how signal move from one flop to another. That is why understanding flip-flop is one of the first steps when learning VLSI design. Before writing the code, let's understand two common types of reset used in flip-flops. The first one is synchronous reset. Here the reset only takes effect during the clock edge. The second is asynchronous reset. In this case, the flip-flop resets immediately when the reset signal becomes active, regardless of the clock. Coming to the Verilog code, first for synchronous D flip-flop, we have three inputs: clock, reset, D, and one output, which is Q. Here, the always block is triggered at the positive edge of the clock. Inside the block, we check the reset condition. If the reset is active, the output becomes 0. Otherwise, the value of D gets transferred to Q. Since the reset is checked inside the clock block, this is a synchronous reset design. Now coming to an asynchronous flip-flop, here we again have the three inputs clock, reset, D, and one output, which is Q. Here you can see that the always block is triggered by both the clock and the reset signal. So if the reset becomes active, the output immediately resets without waiting for the clock. This is what makes it an asynchronous reset flip-flop. After writing the RTL code, the next step in the design flow is synthesis. During the synthesis, the tool converts the Verilog RTL code into a gate-level hardware. For a D flip-flop design, the synthesis tool typically maps the RTL into a standard cell flip-flop from the technology library. In the synthesis report, you will see things like number of flip-flop used, number of combinational logic cells, area utilization, timing information. For a simple design like this, the synthesis result will usually show one flip-flop cell being used. Sometimes the reset may add a small amount of combinational logic as well. Looking at the synthesis netlist helps us understand how our RTL description is translated into an actual hardware component. Now, coming to the synthesized output, for a synchronous flip-flop, a combinational logic has been added on the input line D. We can see a mux here, where the select line of the mux is reset. So if the reset is 0, the mux output is D. If the reset is 1, the mux output is 0. So the output of the mux gets transferred to Q at the clock edge. Now coming to the asynchronous flop, here we don't need to have an additional combinational logic as we required for the synchronous flop because the reset here is asynchronous. So when the reset becomes active, the output Q immediately becomes 0 irrespective of the clock. One important thing to remember in a real VLSI design is the choice between a synchronous and asynchronous reset. Synchronous reset is often easier for timing analysis, whereas asynchronous reset can respond immediately but must be handled carefully to avoid timing issues during reset release. So you can use either a synchronous or a asynchronous reset depending upon your design requirements. So in this video, we learned what a D flip-flop is, why it is important in VLSI, how to write Verilog code for synchronous and asynchronous D flip-flops, and how the design looks after synthesis. So if you found this helpful, subscribe to VLSI for everyone for more beginner-friendly VLSI content. Thank you.